Hi all, welcome back. So today we are solving the one more question related to control system PYQ GATE exam. So this question related to EC exam, electronics and communication engineering. They asked this question this year. 2025 GATE exam. All right. So this question. Let me go through the question. Hope this series is going to helpful to understand the concepts, important concepts generally frequently asked in the GATE exam through the questions, and those are interested to understand the control systems. So this series also going to helpful. All right. So let us read out the question. So they let GS is equal to 1 by 10 s square, the transfer function they given. Okay, and be transfer function of second order system. Okay, and the controller ms is connected to the system in the configuration shown below. All right, and consider the following statement. There exists no controller for the form of ms equal to k by s. This is basically pure control, pure integral control. Okay, so it means for this our given system 1 by 10 s square. So for this whether pure integral control is possible or not for any where ki is a positive real number. This again integral gain we can say such that the closed loop system is stable. Okay, if you put the controller here, this is like ms, and this my plus minus, and this my we are making a control closed system. This is my plant, yeah, process we can say. Okay, so this is my output and this is my reference. Okay, so for this given system whether the pure integral control is possible or not, this we need to tell, we need to understand, and we need to find out. Okay, and second they given there exists at least one controller for form of kp plus skd. Okay, so it means this is a pd controller, right? So this is a pd controller for given system, given process, whether at least any pd control is possible or not. So okay, so a kp and kd are positive real number such that the closed loop system is stable. So okay, they given which of the following option is correct or not for this both of these. So this is our closed loop transfer function. All right, so this is our functional block diagram. Okay, okay, so here this is rs, this is reference input, by s is our output, and ms is here we are a control transfer function. So here we are basically we are analyzing the our type of controller based on our given system. All right, so here basically uh, a pure integral I'm talking about, and second one is our pd controller. All right, if we know the our if you know the our understanding of controller, okay, based on given system, straight away we can say which option correct or not. Okay, as we know in case of integral it adds the one pole at origin. Since our system itself has the two pole at origin. Okay, so it's possible to stabilize this integral nature type system. Actually not possible, right? It again leads to order basically, and it again hence the overshoot basically add the error more, system, because if you add the integral basically it adds the order, it increase the order. When you keep the order, system go unstable. So for given system already has integral nature, right? Because there are two types, the two second order integral we can say, right? 1 by s this is first order integral, and 1 by s ka this is second order integral. Again we are saying for this system, the integral controller is possible to stabilize the system? No, not possible. So again we we have to go for such controller which can compensate this integral controller. So of course which control required? PD control required. Okay. So for this first option anyhow they told that there no exist controller for the form of integral pure integral. Okay. For this making a system closed loop system to be unstable. Okay. So this is correct. And there exists at least one controller form ms equal to kp plus skd, where kp and kd are positive real numbers, so such that the closed loop system is stable. Okay, so it means this is this is possible. At least one control is possible, but like how we can ensure it whether it's possible or not, we can find out closed loop system, closed loop transfer function, and then again see the Raoult-Hurwitz criteria. Okay, whether first we need to look into whether is making their ideal Raoult-Hurwitz criteria, no coefficient should be missed. Okay, if any coefficient missed, then we can say okay, this is not possible. All right, so hope so. So here which option correct? Actually I think D option correct. Okay, both are true. For given integral nature system, integral control would not helpful to install the system. Okay, so before to solve this question, let me go for overview of this concepts. Okay, so here since we are analyzing the type of controller, one is a pure controller and second one is our PD controller. So here let us understand what is a type of integral controller. Okay, so here integral controller, you can see here integral controller, and integral controller is type of feedback controller where the control signal is proportional to the integral of error over time. Okay na, so we have to proportional to integral of error over time. So basically this is my et 0 say t, and we have to multiply the again. Okay, if you convert in the Laplace domain we get ky s. So this controller accumulates the past error to eliminate steady state error. All right. So commonly used in PI PD in commonly we have to use here. Okay, PI PD PID controllers. So property of integral controllers. Actually, this is like type of low pass filter. Wherever all low pass filter this also have integral also behave as a low pass filter, because if you make a low frequency region it passes the signal, high frequency region is abstract, it does not allow the signal. Okay, so that's why, because here you can see 1 by s. So if you put this by 1 by s omega low pass filter. Okay, and then this is low pass filter, right? And one more thing actually here, pole at origin, it adds the pole at origin like 1 by s. If you put add again integral, basically we are adding the one pole at origin in a case of open loop transfer function. Okay. And in case our in case the system type, okay, of course in case of open loop transfer function, and the number of poles at the origin is also called the type of system. Okay, so basically in case the type of increase 1. Okay, so type will be increase 1. Okay, like if you given system is 0 type, so if you add the integral it 1. If given system 2 type, so it will be 3 type, 3 type actually. Okay, improve the switch performance. Response depends upon accumulated error over time. Okay, So that's the things. Significance control system eliminates SDC error for step inputs. Okay. So one more point actually I want to add here. Error is also depend upon type of inputs also, like whether it is a step input, a ramp input. Hope you know the test signals. Okay, like this is step and this is our step input, this is ramp input, this is parabolic input, right? So we have to test out for which for given type of system, for given type of inputs, error is finite or zero. Our intention that we have to error should be make zero or finite. It's not infinite actually. Okay, yeah, maximum. Essentially, in application requiring long-term accuracy, if you require more accuracy, we like speed control, temperature control, we use the integral control. Okay, to use reject constant disturbance. Okay, in case of constant disturbance, we have to use actually like because constant disturbance it will be get added up over time. So in case of integral action, it will be increase. So that's why we can say integral control used for constant disturbance rejection. Enhances the accuracy but may reduce speed of response. Of course, like it lacks the response actually. Okay, it delays the performance, but accuracy will be increased. All right. So this is like trade-off kind of nature, right? So what is the advantage of the our integral control? So this is a zero steady state error for step input. That's important, right? One by yes, you know that like type of this is type of one system, right? If you put a step input, it means limit step zero, you will get the zero steady state error, right? How? Let us this is a steady state error for the step input. Okay. So how we can find out? You know, steady state error like what is a KP, KI, like position constant, velocity error constant, you know, acceleration constant. Okay, I will not go more deep here, and but once related question will come, we will explain more. But point is that step input type 1 system error is zero error actually. Okay, all right. क्योंकि 1 by s square. Okay, and s cancel out. 1 s will be 0. So s 0 it will be infinite. Then 1 by kv you will get 0 error. All right. Okay. So useful in rejecting constant disturbance. That's a very important and improve long-term performances and simple to implement. All right. But demerits also there actually. We need to careful rather than go the stable system go to unstable also. All right. So that's important. You need to take care actually. So here, one more thing actually here I want to tell here like may cause slow system response. In case of integral, generally we don't want to like system our performance we want fast. That time we have to avoid the integral. Okay. So based on our application, based on needs of performance, we need to choose the controller, right? So it delay the response. So here, yeah, lacks the response can lead to instability in high order system. You know, like as you know, our given system is 10s square. If you add again integral, okay, already make sure that our given system is if has the integral nature. Don't add the again integral. Okay, don't choose the pure controller at least. Okay, so because again it leads the higher order, so which cause the instability, results in oscillation or overshoot. Of course, high order cause the overshoot or oscillation. If you go more overshoot, of course oscillation will also be increased. Sensitive to integral wind up. Okay, whenever we add the more error over time, add error increase. So this also cause that integral wind up. There is no role of the integral actually. Integral would not work that time. So we need to also careful this actually. Okay, so that's the merits of this. I'm just go through some, like very important concept actually, like intuitive understanding will be developed for this actually. So integral controller improves accuracy by eliminating the iterated error. Generally, in order to reduce and minimize the error, okay, we go for the integral control. But parallelly, same time it will be slow the response. It uses must be balanced with stability consideration, of course, often combined with P and D actions for better overall performance. So rather than go for like pure integral, we use combine P and D so that it can balance, and then we have to max your all performance. Neither like in terms of switch error should be zero. Parallel system is also stable. All right. Then we go for, since here we are they asking two type of controller, so that's why we are and try to understand here. So with this PD controller, so PD control combines the two controller proportional derivative. So based on current error, okay, and this is rate of change of the error. Okay, if you go, you can see like that. So this is KP into error. Okay, if you go more in better way, so you can say delta E by delta T also. Okay, all right. So transfer function, if you go Laplace domain, you will get Kp plus skd. Okay. So here derivative we are putting like initial condition 0. Then only transfer function valued here. Okay. So because transfer function means that like Laplace transform of output to Laplace transform of input provided all initial condition is 0. Alright. So often used in system where fast response needed without register error elimination. Since PD does not disturb the error, error performance actually. There is no role of elimination of error. Okay. Only focus on transient response actually. It improves the transient response. Okay. So basically it adds the 0. Okay. If you add the one like PD controller, so it basically add the 0 and it improves the transient response. Of course, rise time will be reduces and setting time also will be reduces. It enhances stability margin, like in case our frequency response gain margin, phase margin, it will be increased. Okay, but we need to sure but how much we want actually. We don't want too much like margin also. Okay. Anyway, significance of control system predicts error trends or reacts before large errors occur, improves. Okay, error trends, like it tells about the nature of error actually, reacts before large errors occurs. Okay, like because this is like derivative, right? So we have to subtract and divide by dt. So based on the nature of error, it will react. Okay, basically it tells about future, we can say actually. So it improves damping and reduces overshoot. All right. So crucial for system needing fast and stable response. All right. Common in motion control like robotics and aerospace. So merits of PD controller: faster system response, improves damping ratio. Okay, zeta, it will be increased. That's why oscillation will be damped out. Okay, so reduce overshoot and oscillation, easy to tune for transient behavior. No integral wind up here, it does not allow to, it will control the integral wind up actually. All right. So deviation of PD control, of course, any type of control have the demerits also. We need to ensure, we need to take care. So does not eliminate essential error. Like if you want to eliminate the error also, PD will not be any help. Okay. So we go for again controller, I controller. So we need to include PID controller. So that's why most of the industry we use the PID controller because it has the both compensation. But transient compensation, I mean transient improvements or and initial improvements. Okay, essential to high frequency noise is also very like I mean we have to take care. Like if noise there in system, so it will be amplify the noise also. Okay, like sin omega t. Okay, and omega is high frequency noise. If you put derivative, it will be amplify the amplitude, because a omega cos omega, this is derivative, right? So it will be amplify amplitude. So no ideal for system for constant disturbance. Of course, constant disturbance PD control would not help, because constant disturbance D would not any play. Okay. All right. So that's a intuitive understanding. I mean properties of the pure controller, pure integral controller, and PID controller. Sorry, PD controller. So let us go back to question and solve this question by conventional way. And then if you know that, then straight away we can put the answer. Okay. This is a very conceptual question. Otherwise, you can solve. Okay. So what is a closed loop system? Let us see. So CS, this is bias, right? RS, controller is MS, and into GS. By, since this is negative feedback, so plus here will come. In case of stability, we have to go for negative feedback. So MS is first take a pure integral. Okay. So pure integral means Ki by S into 1 by 10 S square by 1 plus Ki by S into 1 by 10 S square. Alright. So Ki by, just solve it, and Ki. So this is our complete transfer function. What is the characteristic equation? 10 polynomial we can say actually here. So this is our ideal Rao-Hurwitz polynomial we can say? No, because here there are two missing terms, right? S square and S. So of course this none of the any Ki values system would stable. There no any one control possible to closed system goes to stable. Okay. So system is, because pure control is here is not possible to system stable. Okay. So first option is correct. No need to put the table. Okay, tabulation table. We need to first be what is a, our necessary condition we should apply first. Okay, all terms should be available first. SQ, S square, S and or constant term. So these are two terms is missing. So of course poles will be lie on the right hand of the west plane. Okay, so system is unstable. So Ki is not possible here to make system stable. Then we take go for the PD controller. Let us see. So here is a, this is a 1 by 10 S square, right? This is a very good question to understand and analyze the controller. So here again we have to solve for this again closed system for the PD controller. So this is by S by RS. So here PD controller means KP plus KD into S. Okay, and 1 by 10 square, this is our system. 1 plus Kp plus Kd S by 10 square. Okay, so basically here Kp plus Kd S by Kp plus Kd. Okay, so here in case of stable, we have to take care about the denominator polynomial, which is called the characteristic polynomial Kds plus Kp. Alright, so here if Kd greater than 0 and Kp greater than 0 is given, right, in question. So all positive, of course some this system will be stable. Alright, if you go for a polynomial like Rao-Hurwitz criterion also, the same thing, same condition will be appear here. Like a square, we have to put descending order. This is a 10, this is a Kp, here is a Kd, and if you again multiply and then it will become Kp. If you want our first column of should be stable, I mean pole should be stable, no sign change would be there. So Kd also positive and KP also positive. So in case our PD controller for given integral behavior type of system, is stable. Okay, it able to make a system stable. Okay, so that's a question was given actually. Hope you understood the properties of pure integral PD controller. Since they given two type control, that's why we explain this. Okay, hope you understood. So thanks for watching. That's all.